Can you, well, I hope you can hear me. I prefer not to use the microphone. If you cannot, just let me know. Anyway, so thank you for being here. I want to thank also the organizers of this school. It's very important to mention that this is fully organized by students for the graduate program here at Catholic University. Professors didn't, interact at all with this. This is completely organized by them, and I think it's an amazing job what you have done. It's really incredible. It's so professional. Last night we received an email, the professor, and it was really, it felt like, there was a professional institution behind this organization. So, thank you very much. Thank you, Felipe, well, the whole group. Okay, so I am going to give a lecture on Hamiltonian mechanics. It won't be only Hamiltonian mechanics. There will be many different things. I will start with very simple things. Some of you might find it a bit repetitive, maybe boring. Hopefully, if you make questions, we can interact, and I will be able to know your level. I'm sure there's a very heterogeneous community here. Maybe some of you know a lot, some don't know a lot because you're different stages of your career. So please make questions. Don't be scared. Don't be afraid. If you don't know something, this is fine. This is not. We all go through this process of learning, and you're in a school because you come here to learn. So if you don't know something, it means that you're right. It's correct to be here. Okay, today I will talk about things which are zero, which are constraints, and tomorrow I will talk about things which are infinity, which are divergences. And then my last lecture, it will depend how it goes. It will depend how many questions, how fast I progress. I will decide what the last lecture will be. Hopefully it will be about finite things. So one lecture will be about zero, the other one will be about infinity, and then maybe the last one will be about things which are not either zero or infinity. So I will start with a very, very well-known theorem, which in my opinion is one of the most important theorems in the history of theoretical physics, which is Nether theorem. Nether theorem is a relationship between symmetries and conserved charges. And I will use it, not because I won't be talking a lot about Nether theorem, but I will use it as a motivation to go into this issue of constraints and gauge symmetries. So today it will be really a lecture about the Hamiltonian version, or the Hamiltonian description of gauge symmetries, but I will motivate it using Nether theorem. So the idea, I will assume that you all know classical mechanics, you all know, hopefully, Hamiltonian mechanics, the basic of Hamiltonian mechanics. So you all know, if I write a Lagrangian, which is a function of Q and Q dot, then you know what that is. And there's the Euler-Lagrange equations. But the very, very important theorem that Nether discovered, and I will do the proof here, is that it's the relation So first, it's important to understand exactly what a symmetry is, in the sense of Nether theorem, because a symmetry is not in normal life. A symmetry is like when you have an axis, and then you can see things in different ways, so they look the same. If you have a square, if you rotate a square, you will see the same thing. But in the sense of Lagrangian mechanics, a symmetry is something which is very, very different. A symmetry, so that's the first important point, is to understand exactly what a symmetry is. It's a transformation Okay, so to be precise, so this the idea is that the Lagrangian depends on the function q and the function q dot. This extends to q. You can have many variables. I will do it in the simplest situation, but of course you can have many variables. And the idea is that for one given function, so this is the time t, this is the function q, so I have q of t. So for one given function q, I can compute the Lagrangian. Q is a function of q into dot. Of course, if I give q as a function of t, I know immediately what q dot is as well. And then I can compute, if I know q, and therefore I know q dot, then I can compute the Lagrangian. Now I can come up with a deformation of q. A deformation, I will call it delta q. So delta q is another function. This is delta q, which of course delta q has to be will be very small. And this is very important in delta theorem. We work with infinitesimal quantities. So delta q is another function. Sometimes delta q is understood like delta is actually on q. That's not the right interpretation. Delta q is just a name. It's one thing. Delta q, one character. Delta q is just a function. It's not the variation of q. Don't think of it as the variation of q. Of course, it's a variation of q, but it's good in the brain to keep the idea that delta q is just a function. It's another function. Okay, well, if I have delta q, which is another function, which is very small, then I can compute delta q plus, q plus delta q, and that will be, it will give me here, so this will be q plus delta q. Okay, so a symmetry, delta q, which is a function of t, is a symmetry if and only if L evaluated in q plus delta q, comma q dot plus delta q dot minus L. Here comes a very important implication when I say that delta q is a function. It's nothing but a function of some given function with small values. Then delta q dot is just the derivative of delta q. Delta q is a function. You don't have to worry about whether the time derivative commutes with delta or something. There's no question about that. Okay? Delta q is just a function, and that's the derivative of that function. So if I can prove that for the given delta q which I gave, and then the time derivative is immediately determined, I mean once for the same reason, if I know q, then I know q dot. So if I know delta q, I also know delta q dot. So if I compute this difference, and it happens to be the time derivative of something, which I call it b, then I call it a symmetry. So this is what I call a symmetry. Now, a crucial, really important aspect of this calculation is that, note, this has to be true. Don't ever use the equation of motion or any equation of Q when you're trying to find the symmetry. That's a very important property of the symmetry. Symmetry is a transformation which lifts the Lagrangian invariant up to a total derivative for all values of Q of t. Never use the equation. The reason you must not use the equation is actually what we'll see in 1 second. Okay, that's what what people call a symmetry. And there are many, many examples. I don't want to focus on net theorem here, so I won't give you examples, but please do, if you want to really understand net theorem, you have to work out examples. That's the only way to understand the theorem. But I want to go into case symmetries. But you want to understand why I'm starting with this theorem. Okay, so next, on the other hand, by the way, notice that I didn't touch the time t here. In many books, you will find that the theorem, and then there's a transformation of t, this transformation of t, and a transformation of t. This is not necessary. You can do it, and then the proof of the theorem becomes much longer. And I've seen books in which net theorem is like 4 pages of calculation. And that's one of the reasons that they make a translation in t, which just makes things more complicated, and it doesn't add anything to the theorem. So you will see that I will finish net theorem in this in one blackboard, because you don't need to do that. Maybe I will give one example in 1 second. But let me finish the theorem. On the other hand, we also know so this is, let me, okay, well, actually, this is also an identity that you use all the time when you prove the Euler-Lagrange equations. You want to find the Euler-Lagrange equation. When you do it, you do a translation in Q, then you subtract. This is called the variation of the Lagrangian. You subtract L in Q dot, and this is, by definition of the Euler-Lagrange equation, this is exactly the equation plus a boundary term. So normally, when you say, well, I don't care about the boundary term, and then when you find the Euler, sorry, here, I made a small mistake here. Those are the right signs for the identity to be true. So this is the usual, absolutely standard derivation of the Euler-Lagrange equation. So this is an identity for any delta Q. This is true for any delta Q. There's absolutely no restrictions on delta Q. And the whole point of the Euler-Lagrange equation is that you assume that under arbitrary variations, you want the action to be extremal, and therefore it's very important that there's no, this is an identity for any delta Q. This is not. This is true for, sorry, maybe I should add here. Let me add here an S, which I mean here S as the symmetry, okay? This is true only for a symmetry. This will happen only if this particular variation is a very specific variation that I find, which made this equality true. On the other hand, this identity here is completely general. There are no restrictions on that figure, completely general. So now, what Nete did was to look at these two equations at the same time, have one equation, have the other one, and then realize that there's a very simple thing, there's a very simple consequence you can come up with, is that in this equation, delta Q is completely arbitrary. But what I will do is, let's assume that Q satisfies the equation of motion. Let's assume that the function Q, here there are two functions. Let me go back here. In this game, there's two functions which are completely independent. One is a function Q, and the other one is a function delta Q. They're functions, okay? So here, in this equation, I will make a condition, I will impose a condition on this function, on Q. And I will say, let's assume that Q satisfies the equation of motion. If that's true, then this term disappears. Okay? And I have this identity, assuming that Q satisfies the equation of motion. But there's no restriction on delta Q. I only put a condition on Q. And then I look at this equation, and then I say, well, sorry. And then at the same time, sorry, I'm still here. At the same time, so I assume that Q satisfies the equation of motion, and then this is true for any delta Q. Let's assume that delta Q is the same one which I used here. Because this equation is true for any delta Q. So in particular, I can put an S here, and the identity will still be true. So under these two conditions, now what I have here is exactly what I have there. So the left-hand side is identical, and therefore the right-hand side can also be identical. So this implies the So this is the famous Nete theorem, which I'm going to use as a motivation for what I will be discussing the rest of the lecture. As I want to point out that this is a very simple theorem. You don't need pages and pages and pages, as often in many books. The reason that books make it very complicated is that in some books, not all of them, but in some books, it's because they involve a transformation of T, delta and T. At the same time, they do a transformation of the field and of the coordinate. This is not necessary. I won't go to some, if somebody wants to ask questions about this, please go through that. I won't stop at this point. Okay, so this is the famous theorem that this quantity satisfies the equation d dt of this equal to 0, so therefore this quantity is a conserved charge. And then for any symmetry which I can find, there will be an associated conserved charge. This is, as I said, is an incredibly powerful theorem which has been used in theoretical physics since its discovery is so deep. By the way, Nete wrote two theorems in the first paper. There's a theorem 1 and theorem 2. The first theorem is this one, and the second theorem relates to gauge symmetry. So in the way, in one paper, she understood the role of symmetries and conserved charges, and she understood the role of gauge symmetries in field theory, which basically she discovered that if you have a gauge symmetry, which I will be talking now, you have a gauge symmetry, then there are identities between the equation of motion. And then she clarified the Bianchi identities that Einstein wrote, that Einstein didn't understand very well why he was imposing that condition. And then he was the one who understood the role of Bianchi identities in Einstein equations. In one paper is an amazing piece of work. Okay, so why did I do this? If I want to talk about gauge symmetries, why did I start with this theorem? Well, for the following reason. This is this, let me call it utility, which is this boundary term, whatever it is. So this object satisfies the equation d dt equals 0. Now let's look a little more careful about this. This object here will depend on some parameter. So always, that's experience, always there's a parameter controlling the symmetry. So for example, in the translation, delta Q could be Q plus epsilon. So if you have a theorem, which is invariant under translations, then what you're saying is that if I trans Q plus, delta Q is epsilon, well, delta Q will be some parameter. If you have a rotation, delta Q will be some matrix times Q. Well, let me call it epsilon, which will be an anti-symmetric metric acting on Q. There's always a parameter controlling the transformation. So I will I will write this Q as something times the parameter. That's why I call it Q tilde here, because Q tilde contains a parameter, it's inside. So this will always be, and in the many examples, but you will always be able to put it in the form of something which depends on Q. Basically, you have something that depends on Q times some parameter. And the parameter controls that the transformation has to be small, so normally epsilon will be very small, and it's telling you the strength of the transformation. Now, here comes a crucial point. Nobody is telling me that this parameter has to be constant. This parameter could depend on time, or could depend on anything. So at some point in this proof, at any point, I didn't make any statements about the parameter. The parameter can be anything. As I said, in the case of a translation, delta Q will be epsilon, but I could have a theory, maybe, in which the symmetry is translation invariance, but the translation can be different at different times. So that would be a very weird, very different to, for example, a potential where I write 1 over 8.1 and 2. And we know that this is invariant on the translations, but normally this will have, this would be the potential plus 1/2 square plus 1/2 some masses. So this potential, the potential alone, would be invariant, and the translations that might depend on time. I could say, well, if I displace R1 into 1 plus an arbitrary vector depending on time, and at the same time I displace R2 with the same vector depending on time, this is invariant. Obviously, because this is a minor sign, so they will cancel. But this bit here is not invariant under such symmetry. This will be invariant if epsilon does not depend on time. But if that depends on time, then this is not invariant. So that will not be a symmetry of that Lagrangian. It will be a symmetry if the kinetic term has also this invariant, which is more difficult to find. Okay, why I'm talking about this possibility is because of this equation. Let's suppose for 1 second that there exist symmetries in which the parameter can depend in an arbitrary way as a function of time. Okay, so let me assume that epsilon is an arbitrary function of time. Let's consider it, and I will, of course, many examples, the whole of gauge theories, that's the whole point. But there's a problem here now, because this equation, net theorem, is telling me that the variation with respect to time of Q tilde has to be 0. But if this is a completely arbitrary function of time, I have a problem with this equation. So if I compute this, I will get Q of the t times epsilon plus the Q epsilon of the t equals 0. So I might say, well, Q is the thing which is constant. So this is 0. But then I have Q here times an arbitrary function of t. So there's a clash. The only solution to this problem, which is not really a problem, is that Q has to be equal to 0. So this is the way that net theorem includes the way gauge theories. So the theorem is still valid because in this proof I never use that epsilon has to be constant. It could be some given function of t, that's easy, but we can even consider that the fact that the situation where epsilon is an arbitrary function of t. So if epsilon is an arbitrary function of t, the theorem is still true. But what is the condition it will put is that the charge has to be equal to 0. It's the only way that makes sense of that result here with an arbitrary function. So this is exactly what happens with gauge theories. You apply net theorem, for example, and then what you find is a constraint. So let's go now into that. So the simplest example, the simplest gauge theory, it's not the simplest, but the most well known, is electrodynamics. So let's write down the electrodynamics. haven't heard any questions yet. Is it because it's too trivial?
No.
It's too trivial.
I was actually going to ask you what was the difference between asymmetry and invariance, because I've heard that gauge invariance is not asymmetry because it doesn't lead to a conserved charge, but you answered it just now. So
I'm integrating them.
yeah.
I mean, that distinction is a very important distinction. One, there are two kinds of symmetries. One are called Noetherian symmetries, and the other called gauge symmetries.
Because it was
In the netted case, the parameters don't depend on an arbitrary way on time, and they take you to a conserved charge. If the parameter depends on an arbitrary way on time, then the conserved charge is equal to 0. But now what we're going to see now that the fact that the conserved charge is equal to 0 actually is a crucial aspect of gauge symmetries, and that's very clearly seen in the Hamiltonian forms. Okay, so okay, so QED, this is the simplest Lagrangian with a gauge. Not the simplest, I say, it's the most well known. There's much simpler gauge theories, but this is the most well known example of a gauge symmetry. We all know that this is invariant under what F mu. Let's keep on mu. And then this is invariant. And this is an arbitrary function of all coordinates. So this is a situation in which I have discovered a Lagrangian with this huge symmetry, in which the parameter of the transformation is an arbitrary function of the coordinates. This is, as I said, this is the most well-known example of a gauge symmetry. I want you to keep in your brain the following fact, is that the time component here, delta is 0, involves the time derivative of the parameter. Okay? Just keep it in mind. We'll come back later on. This is an important, of course, I could also write the fact that the space component, of course, transform like that. But this, believe me that this one, the way is more important. Okay, so this is the famous Lagrangian from Maxwell equations. What I'm going to do is to write them in a Hamiltonian way. Now, before doing that, I want to put emphasis on something which is often not really well understood. Is the relationship between Hamiltonian mechanics and Lagrangian mechanics. Often, there's this idea that somehow you start with a Lagrangian and then you find the Hamiltonian. This is not correct. They're both at the same level. You can start with a Lagrangian and then find the Hamiltonian, or you could start with the Hamiltonian and find the Lagrangian. They're equally, well, they're both equally important, of course, but it's not that somehow the Lagrangian is here and the Hamiltonian descends from the Lagrangian. That's not correct, okay? So you can go both ways. We'll do that exactly in this theory. So what I want to, maybe I should leave this for the whole lecture. Normally you write the Lagrangian action. This is a function of Q. Or this will be the Lagrangian action. Or you can write the Hamiltonian action, which is a function of Q from T. There's two sets of variables. And this is Q, P to dot minus H. And then I write them both at the same level, making stressing that point. It's not correct to think that you start with this one and then you derive that one. You could have started with this one and then derive that one. You can go both ways. It's completely equivalent. In this one, the only Lagrangian equation, we all know them. And in this one, you'll find Q dot These are called the Hamiltonian equations. So you can, yes?
Can you have one without the other?
One and not the other?
Yeah. Having Hamiltonian, but not having the variable is not perfect.
Maybe some exotic system. What it does exist is multi-Hamiltonian theories, for example. It does exist. I don't want to claim a theorem here, but in all standard systems you can go both ways. We can work out the classic, Q dot minus a potential, and that you can go both ways. I can do that in 1 second. I'm not sure what would be the general answer to that question, really. I don't know. I don't think so, but I don't know. Sorry, yeah, that's the answer, I think. Okay, so this action here has far more structure. There's far more things you can do. And what I want to show you here is today is that you can understand gauge symmetries in one go for all of them. It's just one statement which has to do with this, what we found here, the presence of conserved charges, that the values are equal to 0. And that's the main ingredient of a gauge theory, and that shows up very clearly in this formulation here. But I want to make also the point that you can go from one to the other and vice versa. Okay, so very quickly, let's go for something. You start with this one very quickly. So suppose that H was E squared to M plus some potential of Q. So this. I give you this Hamiltonian. I say, let's start with a Hamiltonian theory in which the Hamiltonian has this form. And this is my starting point. And then if you know Schrödinger equation, then you know very well that this is exactly, and then you multiply by H bar, replace T by H bar in Laplacian. This is exactly the correct operator with the Schrödinger equation. So this is not something that hasn't appeared in the literature. So if I have this, and then I look at this equation, Q dot is equal to P divided by M. In other words, P is equal to M Q dot. This is an equation, of course, we know very well. And if I replace P is back into the action, what you will find is exactly, I won't do the calculation, but you will find exactly where P is. Use that expression. I'll let you do the math, it's very simple. Just saying that I start with this action, with this Hamiltonian, and then I use this equation. I will be a bit more precise. I need to insert one more sentence, but let's do what the algorithm is. Okay? The algorithm is use this equation of motion, and this equation for this Hamiltonian is simply Q dot equal P divided by M, and therefore P is equal to M Q dot, something that you expected probably. And if you replace P in terms of M Q dot here, you do a little bit of math, and then you will find this, which of course is the Lagrangian formulation. I just want to make the point that you can go from here to there. You don't have to go from here to there. You can go both ways. Now, one thing which is crucial here, and I hope that you all pay attention to this sentence. In general, you don't solve equations and replace them back into the action. That can be done in only one situation. Is when the equation, when you vary with respect to one variable, and then you can solve that variable algebraically. It's the only situation where it is correct to replace back into the action. Okay, this is exactly what this equation is. This is the equation that follows by taking the variation with respect to P. I vary this action with respect to P. Okay, and I get this equation. And this equation happens to be algebraic for P, because it's this equation here, which I can solve for P. Then I can replace back. Okay, so don't do that carelessly. You have to be very careful with the actions. You don't solve the equations and replace them back into the action. Unless you want to know the value of the action for a given solution. Of course, you can do that. You can solve the whole system, you replace back, and then you want to know the value of the action for a given solution. That, of course, you can do, but you cannot vary that action afterwards. That's forbidden in general. The only situation, there are two situations that you can do that. One is this one, in which you vary with respect to one variable, and the equation motion when you get can be solved in an algebraic way for that variable. Then you can replace back, and you will get something which is consistent. And the other situation is when you have Lagrange multipliers, that they can also replace back into the action. Okay, so this is just to make the point that you can go from this action to here, and I want to apply this to electrodynamics. Because you might be wondering, well, what's the Hamiltonian version of it? This is the Lagrangian. This depends on A and the derivative of A. Actually, it doesn't really depend on A, it's only the derivative, but this is the Lagrangian. So what is the Hamiltonian? What I will do is that I will give you the Hamiltonian action, and then I will give you what the steps are in order to bring back the Lagrangian action. So let's do that quickly. So the Hamiltonian version it has the following form. It's a momentum times so this is, I give you this action. This is an action in field theory now. We are in field theory, we're not in the particle anymore. So there are four integrals here, time and space. So I have a vector. Sometimes useful to use the vector notation or an index. You can use whatever notation you want, but I have a vector which is the conjugate. By the way, so, well, I can discover it later on, but you will see here, there's AI here, and then there's A0 here. So you might have a suspicion, these two things will form A mu, which is the space-time relativistic moment. Sorry, gauge field. But I give you this action, and I claim that this action is completely equivalent to this one. It's exactly the same action. You can say, well, how do we prove it? Well, exactly in the same way. Let's take the variation, let's take the equation of motion with respect to P. And then, sorry. No. We'll do, that's right. I will take the equation of motion with respect to P, and I will show that that equation is actually algebraic with respect to P. So I can replace it back, and then I eliminate P, and then, yeah, this is exactly that. I will not do all the details, I will just show you more or less how it works. Then you can fill up the minus sign and the factor of 1/2, etc. But the main point is the following. Let's take the variation with respect to P of this reaction equal to 0. So clearly, if I vary here, I will pick up the time derivative of A. Here, I will pick one momentum, Pi. There's a 1/2 P squared, so I get, and then I use back the notation with an index. And from here, there's an integral. Here's the divergence of P. I will pass the divergence to A0. I will get minus sign in I is simple. This is equal to 0. So this is the equation of motion. When I vary this action with respect to the momentum P. I'm sorry, I'm using sometimes the vector, sometimes with the index, but you're all grown up, so you have to be able to go from one to the other. Now this equation is algebraic with respect to P. So from here, I can write P, the solution, P, I pass everything to the other side. And I will use now this other notation, This is the IP of AI minus. And then you should recognize an object. This is the component. This is F0I. This is the Maxwell tensor. So this is, here appears the gauge potential, the spatial component, here the time component, and here I have the derivative with respect to x, and here the derivative with respect to t. This is exactly this combination here applied to the time x component. I have this, but let's forget about this. This is what I get. P is equal to that. So now you're allowed, only because I took the radiation with respect to P, and this equation happens to be algebraic with respect to P. Then you're allowed to take this P and replace it back here. Okay, everywhere where you see P, instead of P here, you replace this expression. And then P disappears completely. So now the action that will depend only on P will disappear from here, P disappear from here, P will disappear from here. So the action now will depend only on A, this A, and A0. And when you get this exactly back. So if you do the math, of course, you can do it with X tensor in 1 second, for example. I won't do it here. The point I want to make is that many points I want to make. First, you can start with the Hamiltonian action, and the Lagrangian becomes like a so this could be understood as more fundamental in the Lagrangian, which is not correct either. I'm not trying to say that the Hamiltonian is more fundamental. I'm just trying to say that both equally fundamental. You can give the Hamiltonian and then find the Lagrangian, or you can give the Lagrangian and find the Hamiltonian. That's one point. Now let's play with this action. So the crucial why this actually is a good example of a gauge theory is because here we find a constraint. We have a Lagrangian multiplier and a constraint. This is the characteristic property of a gauge theory. The equation of motion here so you have to take I with respect to P equals 0. That's an equation that you already wrote, so I won't write it again. Then you have to take the relation with respect to I equals 0. These two are canonically conjugate. And finally, you have to take the relation with respect to A0 equals 0. This is the one we're interested in now, that will give you that. And this is what is called a constant. And this object is exactly this. So I'll give you as an exercise for you, is to prove that if you apply Nether theorem, I will leave the symmetry very soon, but if you apply Nether theorem to this action, what you will find is a conserved charge, and that conserved charge, which is Q, it will be exactly this quantity. But that quantity is constrained to be zero. So it's a condition, part of the equation of motion of the theory. So you first, you don't solve the equation when you have an action, in principle you have the action, so you don't know that it has to be zero. You just have an action, and you have a symmetry. Then you apply the theorem, and then what it will give you, that the conserved charge, it will give you a conserved charge, and it will tell you that this is the conserved charge. So this is Q for this theory. But then you look at the whole set of equations, and then you discover, oops, this is equal to zero. So there's, in a way, there's no conserved charge. But Nether theorem is equally powerful. It's still telling you the right information. Okay, this is exactly this concept. So what I want to, I don't know how much time. What I want to do is to use the full power of this formalism. So far, what do we have so far? Equality, the important things for Nether theorem is so important. It won't be very important here, but it's really powerful. But what are my message today is first, the Lagrangian and the Hamiltonian are equally important, equally fundamental. Because one go together, or vice versa. But now, a bit more specific, this is an example. I can give you this Hamiltonian action, and then you can discover the Lagrangian form. But now, from here, the takeaway is the following. The Hamiltonian action, for example, gives you, in a very clear way, what the energy is, or the energy density really, in a given system. So the Hamiltonian, I don't want to say the Hamiltonian is more fundamental, because I will contradict myself. They're equally fundamental, but the Hamiltonian is very explicit in some things. It makes some things make them very explicit. Sometimes you might wonder, what's the energy of the system? What's the energy? How can I compute the energy of something? In the Hamiltonian, it's just whatever appears here. You have this is the kinetic term. This has to do with the kinetic term, and then you have the Hamiltonian. Of course, this is also part of the Hamiltonian, but this will be zero anyway. So this will not contribute to the energy. So if you wonder what's the energy density for electrodynamics, of course you can go to Jackson, then you will find a horrible derivation. Eventually he comes out with a formula. If you have the Hamiltonian version of electrodynamics, you're just looking, well, this is P naught minus the Hamiltonian. This is the Hamiltonian. This is the energy density, because there's an integral here. So that's something that Hamiltonian does for you. And the other thing it does for you is that if there's a J symmetry, it will show up as a constraint in the Hamiltonian system. And then this is the role of this part here. So I have this function. This function doesn't appear anywhere else. This PA, BA, this is a cross product, and then A0, there's P here. So A0 only appears here. So it's a Lagrange multiplier. It's a Lagrange multiplier enforced in this equation here. And then what I want to, the last thing I will do is that whenever you have a theory with constraints, that means Lagrange multiplier and constraints, and if those constraints are first class, which I'm going to explain what that is now, then there's a J immediately. Okay. So let's write it up here, and then I will do the proof, and that also shows how powerful. In general,
Professor, I have two kind of stupid questions. The first one is, so you first said that we could have the Lagrangian formalism and the Hamiltonian formalism in equal weight, but then you told us that we cannot always plug back the canonical momentum back into the action.
No, that you can always do. The momenta, the equation for the momenta is always algebraic.
In the Hamiltonian formalism.
Yes, in the Hamiltonian formalism. Well, unless you have, no, it's not always good. There could be some degenerate system in which you cannot do that.
Okay.
But generically you can always, that particular equation for the momenta is generically is an algebraic equation for the momenta.
But
and then you can replace it back into the action, and what you find is the algorithm.
But if we can't do that, then we can't go back to the Lagrangian?
When we start again, then there will be other things to consider. Yes.
Okay. So the second question is, okay, so we have, if we first start with the Hamiltonian...
This is an example where it works.
Okay, yeah.
For the free particle case also, it also works, and generically it will also always work.
Okay.
Except in some degenerate cases where it might not work, and then you have to do more work.
And if we are not starting with the Lagrangian formalism and then going back to the Hamiltonian, how do I construct this if I don't know the Hamiltonian?
Okay, good. So I don't want to do it now because I don't have time, but you can start okay, very quickly when you do the following. So this is the Lagrangian, okay? When you do, you have to do what is called the 3+1 splitting. When you split these variables into the time.
Yeah. But you're starting with the Lagrangian.
Yeah. And then you define the momenta.
Yeah. But if we want to start from the Hamiltonian, because you said that we could start from the Hamiltonian and
No, you decide. If you give me the Lagrangian,
Uh-huh.
then I can define the momentum in the usual way, and then I will find out.
Okay, but that's
If you
still.
give me the Hamiltonian,
Uh-huh.
then I take the equation of motion with respect to P, replace pi, and I find out.
Okay. Yeah. My
That's
question was-
they're both equally.
Okay. But there's not a way to find the Hamiltonian if we don't know the Lagrangian. That's the.
And there's no way to know
Yeah.
the Lagrangian if you don't.
Yeah, that was my question. Yeah. I know the way to do
Exactly.
this.
Normally, I'm making this point because normally people go from here to there. And I
Okay.
give you the impression that this is more fundamental. But there's system in condensed matter physics, in quantum mechanics. Quantum mechanics, normally you know the Hamiltonian.
Yes.
You don't know the Lagrangian. Quantum mechanics, the Lagrangian is something that you don't look at.
Yes.
The Hamiltonian is the fundamental thing. And then if you have the Hamiltonian, you can build it. Just want to put them both at the same altitude. Now, the Hamiltonian does have more structure. There are some brackets, many things you can define, which actually are very helpful, and they give you a lot of information. Like the energy density, for example, it's very easy. You have the Hamiltonian, then you have the energy density, which is a fundamental quantity that you want to understand. In the Lagrangian, you have to do a bit of work in order to understand what the energy density is. Okay. So, general form of a gauge theory. The Hamiltonian form. So this is something you can do in the Hamiltonian and not in the Lagrangian. Of course, you can do it, but it will be complicated. Because as I said, anything you can do in one, you can do in the other. But in some it's like the energy density. Of course, you can come out with what the energy density is if you start with the Lagrangian. Of course, you can. But you have the Hamiltonian. It's just, you look at it and it's right there. Okay? So this is the point I want to make. So I will consider some theory with a lot of variables. I will consider the more general case, and then we'll work out the details in a simple case. But a general theory which will have some index here. This index might be continuous or discrete, so I'm considering field theory. If I have a field theory, then I will say that A is really a continuous index. So there are many P's and many Q's, which might be infinite number. There's also some Hamiltonian, which I will call 0, which is a function of P's and Q's. 0 because there are the pieces here, and then I will consider some constraints. The functions of the P's and Q's. And I will split the constraints in two sets, different sets. So I'm taking as motivation this action. So look at the Hamiltonian action for electrodynamics. So this is a kinetic term, and then this is what I'm collecting here now, some general kinetic term. There's also some Hamiltonian, which gives me the energy density, which is what I will call E0, with some depending on the theory. I will write a list of theories which fall into this structure. And then I have Lagrange multipliers multiplying constraints. But I will consider first many possible Lagrange multipliers. In this case, it's only one, E0. I will consider now many cases, and I will split this in two sets, which I will explain now. This, by the way, this was all done by Dirac. Dirac is that this is called the Dirac formalism. Dirac went through from the Lagrangian. It's a painful construction, and I come up with this final answer. I will do it the other way around because it's more fun and easier. Let's start with this, with that motivation. So this is my motivation, this action. Of course, it's very important. By the way, Yang-Mills theory, with no extra cost, Yang-Mills theory, you only have an index here, an index here, there's an index here, and an index here, and then an index here. It's exactly the same action. The Yang-Mills action in Hamiltonian form is exactly the same. You just have to add more instances. Okay, so the conditions, of course, these are constraints. So these are, okay, I will have to vary here with respect to Q, P, lambdas, and mu's. Okay, so these are constraints. These are forced to be 0. And this also are forced to be 0 because of the equation of motion with respect to lambda and with respect to mu. will give me the phi is equal to 0 and the chi is equal to 0. When I will make some assumptions on some of the properties, and then I will distinguish what they call first class and second class. And then I will make an example of the first class, which is the most important one. So let's assume. So this is, by the way, this. So I give you this theory, just like I can give you Lagrangian. Nobody complains. Normally I give you this Lagrangian, and then I write the equation of motion. I solve them. I find black holes. I find the asymptotics. I find the of charges, the entropy. You just give a Lagrangian. I say, well, instead of giving you a Lagrangian, I will give you a Hamiltonian action. In this case, it means give you some function of P's and Q's, some functions of P's and Q's here, and some other function here. I just give it to you. With some function. And then I say, work out the details of the theory. So I will now claim that if these functions, this one, and this one, are cleverly chosen, then this theory has a gauge symmetry. And then, of course, this includes, by the way, general relativity force in this class, Young theory force in this class, Chern-Simons theory force in this class. So all theories, just name one theory, and I can write it in this way. So the theory I will show very quickly now applies, or the way considers or put all theories in just one bag. That's what is important about the Hamiltonian formulas. Okay, so if phi alpha satisfies the following conditions. First, the Poisson bracket, the phi's with themselves have to commute. Now, if they satisfy a closed algebra with respect to the Poisson bracket, if phi alpha with H0 also, let me call it K alpha gamma B and if I alpha with respect to chi, C alpha plus C J. Then this is what is called the first class constraint. It's first class. So if this guy is over here, of course, you will say, well, why is this? What are they doing here? I will explain in 1 second, okay? But this set here, I will claim that I can choose them very cleverly, such that the Poisson bracket with themselves gives something proportional to themselves. And actually, you can even include here something proportional to the guys, but let's keep it simple for the moment. The Poisson bracket with H0 is also a combination of the constraints, and the Poisson bracket with chi is also a combination of the constraints. If all these conditions are satisfied, then I will say that there's a gauge symmetry. And then you can use Nether theorem, for example, and find the generator of this gauge symmetry, or find the conserved charge, which is actually the same. I won't be able to solve that, I don't have the time, but you can use Nether theorem and then try to find what is the conserved charge associated with the symmetry, and the conserved charge will be exactly phi, the constraints. Okay? So I will prove this in the simplest case, in the simplest case. I just want to display the full theorem. Now, what's the distinction between the phi's and the chi's? If the chi's precisely don't satisfy all these conditions, the chi's are called second class, and the main property of following is that the Poisson bracket with himself is an invertible matrix. And these are for second class. You may say, well, what if that matrix is not completely invertible, but there's one component which has zero somewhere? Well, then I take that constraint and I put it here. Okay? So the idea is that you have already separated those constraints that commute with themselves, it's called commute weakly. If the constraints are zero, then this is 0, 0, 0, 0, 0. So they fine commute with themselves, commute with the Hamiltonian, and commute with the guys. They have to commute with all of them. Otherwise, they won't generate zero. They have to commute with all of them. And the chi are exactly the opposite. They don't commute, not even with themselves. Actually, I don't bother writing the rest because it's not relevant. Once this condition happens, they will have a set of constraints. They are constrained, but the Poisson bracket is an invertible matrix. Then underneath there is second class. They don't generate a symmetry, and they will play a completely different role. So the role, the difference, is the following. Okay, so the important point here is that, as I said before, all GH theories fall into this classification. And then we will be able to prove GH invariance in this general setting, and therefore we are proving GH invariance of general relativity, which includes all of them in one go. It just is a generic, generic structure. You don't have to go example by example. Just the only thing you need to prove is, of course, that the constraints satisfy this condition. And once you know that the constraints satisfy the conditions, then you will know immediately whether they're first class, second class, and whether it's a GH into or not. Okay, the main difference between the first class and second class is called consistency conditions. Obviously, for the equations lambda alpha mu e imply, somehow repeated, but anyway, is imply that the alpha, which are functional of the q's in the p, equal to 0, and the guys, which also some function of the q's in the p, are equal to 0. This is something that, up to this point, there isn't a big difference between both of them. This equation of motion will force this constraint to be satisfied. Now, what the Dirac pointed out is that when you look, if you look at this has to be true for all times. It's not an initial condition. This is an equation of motion. It has to be true at all times. So if this is true, then this implies that the time derivative has to be 0 right here. Has to be 0. And this, once you write this, then you discover the big difference between the first class and second class. Let me write the 0 at the left side, so I can come. This is plus. So what's the main difference between one and the other? And this, by the way, this introduces the notation, the famous notation, the Poisson bracket notation. It's so useful. Maybe I should write this here. If you have some function these and q's, and you want to take the time derivative, so you say, well, this is the a, the p, p dot, the a, and the q, p dot. But then I will be interested in those p's and q's that satisfy the equation of motion. You might not, but if you're interested in the p's and q's that satisfy the equation of motion, then I write this. And this is exactly what is called the Poisson bracket between it's just a notation. It's a very good combination. It's just notation, but it is very useful when you're taking time derivatives. You take the time derivative of function of p's and q's, And then if you assume that the P and Q satisfies the equation of motion, then that time derivative is precisely the time derivative with respect to the Hamiltonian. Now, the Hamiltonian in this situation is the whole thing. This is why I call this one H0, okay? This is the Hamiltonian. This is the kinetic piece, and then the rest is the Hamiltonian. Now, this will not contribute to the energy, because this is constrained to be zero, this is constrained to be zero, so the energy will not really see them. Okay, but they do take part in the equation of motion. Okay, so using this notation, the Poisson bracket notation, then what I have to compute here is phi alpha with H0 plus the equal now lambda beta mu j j. This is the time derivative of the constraint, and then here is the same thing. It will be the Poisson bracket.
Professor? Why aren't there second class constraints with a zero component? Because it's solely I components?
No, sorry. This is not relativity here. No, this is
okay. It's just a different index.
Yeah.
Okay.
No, I has nothing to do with
So
special
okay.
index. This is just not because I don't have more letters.
Okay.
I use A for P1, P2, P3.
So Latin letters and Greek letters
for
the same.
alpha 1, and then
Thank you.
I go use Roman.
It's okay.
Okay, so what's the main difference then is quite clear. Why first class are very different from second class? It comes from this condition. So the first class constraints, they have to be zero for all times. That means that the derivative with respect to the constraint has to be zero. That derivative is equal to amount to compute this Poisson bracket. But as I said before, the Poisson bracket of phi with the Hamiltonian is basically zero because it's proportional to the constraint. With the first class constraint with themselves is also basically zero because it is proportional to the constraint. And with the second class is also zero. This is a condition of the depot. So this is pretty much just zero. This we use normally the notation weakly zero, referring that it's not zero for all P's and Q, but for the P's and Q that satisfy the constraints. So this is just zero. But this one is very, very different because this will be whatever it is. Chi with H0, actually whatever it might be, doesn't care, will be something, plus that one will be something, I don't really care. But then I have this one with that one, and that will give me mu j times the matrix ji. Okay? And this is an invertible matrix. And this has to be zero. So this condition, this fixes this Lagrange multipliers. Okay, so this will fix. So the second class constraints have their Lagrange multipliers, which are the mu's. The mu's are the Lagrange multipliers, but the consistency of those constraints, it will give you it's a consistent condition. This will be some the Poisson bracket will give me something, I don't care, it will be some numbers, but then I have the mu's multiplied by this matrix. And this matrix, by hypothesis of second class, is an invertible matrix. And if it is invertible, that's of course I can invert it. Mu I will be times something. This is the inverse problem. While the first class constraint did not impose any condition at all. They are, by definition, they will be satisfied in time. That's the big difference between first class and second class. Now, why one imposed a gauge symmetry and why the other ones don't give a gauge symmetry? Precisely for that reason. The mu's, in this case, they're completely determined by the dynamics. So they don't impose an arbitrariness in the time evolution. This is, by the way, this is the class of constraint if you go to Goldstein or whatever, books in elementary mechanics. In a way, when you take this big thing rolling down, etc., with a Lagrange multiplier, the Lagrange multiplier gets fixed by the dynamics, by the equation of motion. This is exactly the situation with the second class constraint. Those are second class constraints in that respect. And there's no gauge symmetry. You never heard of a gauge symmetry when a big thing is rolling down a mountain. And the reason is that they are second class constraints. So the mu's are determined by the dynamics. There's no arbitrariness. Completely different is the situation with the first class constraint, that they have Lagrange multipliers, like these ones, alpha, and they don't get fixed by the dynamics, because the constraint is satisfied at all times imposing no conditions at all. That means that when I solve the equation of motion, there will be these functions will take any value I want, and that's the signal of a gauge symmetry. When you have some equation of motion, that there's some function that don't get fixed with the equation of motion. This is what a gauge symmetry is. Okay, so let's now depending on the 15. I think we'll leave for tomorrow the proof. I don't want to prefer to take questions. So what? Okay, so this is, as I said, this is a very, very important line. Yeah, the distinction between first class and second class. Second class also, when you buy a ticket, first class or second class, it's a big difference. I think they call them second class for some reason, because those ones are not very important generally. The first class, they're really important. And they play an important role. And the second class, normally you try to get rid of them one way or another. But in some situations, you do get second class. So if you have a system of this form, the first thing you want to do is to compute the Poisson brackets of these guys with themselves and with the others, and the Hamiltonian. And then you can separate them into first class and second class, and they will play very different roles. So what I will do tomorrow is that we'll do in the simplest example. Okay, I will erase the Hamiltonian and I will erase the second class. Okay, just to make the calculation as simple as possible. The calculation with the whole thing is exactly the same, just longer. And then we will prove that if this constraint satisfies a closed algebra, the other ones will not be relevant. If this constraint satisfies a closed algebra, then there's a gauge. Okay? And the proof is very simple. And the good thing about it is that, in a way, you're in one step, you're computing the gauge algebra of general relativity on gauge theories. Okay, questions, please. Let's stop here, and then I will do that tomorrow. Yes?
Could you go to the second? Did you go to the second board? Pull up the board, please. Okay. I don't understand too well how this the first equation, the time derivative for p is weakly zero. Can you explain again?
Sure, it's yes. So this is for the condition that I apply here. So I assume when I give you a Hamiltonian action with a gauge symmetry, I have to give you H0. It's just like if I give you Lagrangian, I only give the Lagrangian, I know it's only one function. In the Hamiltonian, you normally give the Hamiltonian and possible constraints. Okay, I just give them to you. I will tell you, look, this is some given theory with a given value of H0 as a function of P's and Q's, which would be P squared plus Q squared, which is, by the way, the QBD has exactly that form. And then I have to give you this function of phi alphas, some number of them, and the other ones, some number of them. So then I'm saying, if the phi's satisfy these three conditions, if they don't, then there won't be a gauge symmetry. If they satisfy these three conditions, then the claim, which I will prove tomorrow, is that there is a gauge symmetry. But before proving the gauge symmetry, I'm just letting you see that there's already a big difference, an important difference between this one and that one. This one has to be 0 for all time, therefore the time derivative has to be equal to 0, and the time derivative on shell I'm interested in the time derivative once the equation of motion is satisfied, so that means computing the Poisson bracket between this and that one, and then phi with h0, I look at my table, and then phi with h0 is proportional to phi plus chi's. But those are constrained to be 0.
Oh, okay.
As simple as that.
I understand that.
And then that one with that one
Zero.
is exactly the same.
Yeah. Thank you.
And this one, then you pick up the invertible metric here. Okay, let me maybe also tell you that there's a recent paper, well, not that recent, but there's a recent paper by Wheaton dealing with the ADM formulation of general relativity. I'm just saying that even people from deep string theory, they keep in mind this formulation of general relativity. This was done in the 60s, 70s. This is very old-fashioned in a way, but it comes up from time to time, and with a really interesting development. There's a recent paper by Wheaton trying to find the general solution to the constraints, because it is understood that if you know the general solution, then you know a lot about the theory. There's also a paper by Maldacena in the 10, 15 years ago, where he used this formulation to compute the correlator, the higher point functions in cosmology, and then he came up with a formula for non-Gaussianities, which is a big issue in cosmology, using the ADM formulation. So I'm just saying that even though the ADM formulation was worked out a long time ago, that was, I think it was 58, 60, 61, Arnowitz, Dessert, and Misner, I think they're all dead right now. Misner was another guy, I think a year ago. It is a formulation which is always showing new ideas, new results, and I think every theoretical physicist should know it. That's why I decided to at least spend one lecture on this, because it's very important. It's something that gives results all the time. More questions? We have.
I'm sorry? So the reason that this is like approximately 0 and not equal to 0 is because we need to be on shell? Or?
Yes, exactly.
Okay.
Yeah, that's this notation. This is called weakly 0.
Weakly
In the sense
zero.
that it's 0 if the constraints are 0.
Okay.
That is just notation. It's not strictly 0. It's only 0 provided the constraints are satisfied. Okay, so keep in mind this consistent condition, the difference. So the very important difference between this one and that one is that this one, this condition does not give you any conditions. It just is satisfied by the assumptions done on the phis. So this is just 0. You compute it and it's 0, so you put it aside. Okay, I don't have to look at it anymore. But this one gives you conditions on the Lagrange multipliers. These ones, they get fixed. And that is the crucial point, because that's the difference between having a gauge symmetry and not having a gauge symmetry. You have a gauge symmetry when the time evolution have functions which you don't know how to fix. They are arbitrary. Then you have a gauge symmetry, you have to put gauge conditions. If all functions get fixed by the equation of motion, once the initial conditions are given, then there's no gauge symmetry. So these ones do not generate a gauge symmetry, not because the Poisson bracket are that. No, the reason they don't generate a gauge symmetry is because the Lagrange multipliers are fixed by the denominator. These are not arbitrary coefficients. Well, these ones, these lambdas, don't receive any condition. They become completely free. And that's the sign of a gauge symmetry. Of course, we need to work it out, and then that's what we'll do tomorrow. Okay, are we done? Or I have no idea whether it was too simple or too complicated. I will continue at my.
Any more questions?